Get everybody's attention. So in section 4.6, we're talking about geometric sequences. Oh no? Oh no, 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 no. All right, so I'm actually going to start with some of the homework assignments that apply to what we learned yesterday. And then I'm going to go into showing you the explicit formula for geometric sequences. So remember what we talked about yesterday was the recursive formula. So right now I'm going to work on write the first 5 terms. I'm going to work on number 11 through 14. No, let's do a number 11 and 13 because that's my odd ones. And then I want to look at 23 through 27 odd. You did learn the recursive formula for geometric sequences. What is the geometric sequence recursive formula? Anybody? You blocked yesterday from your memory? We learned the recursive formula. That was the first one. AN equals R, right? And so AN is the term at position N that we're trying to calculate. We're trying to calculate what the term is at whatever position N. AN minus 1 is the previous or preceding term. So it's the term at the previous position right before the one we're trying to figure out. Multiplied times, what does R stand for? Yes, that's our common ratio. So this is very similar. It's sort of a mirror to what we saw for arithmetic, except with arithmetic, the formula for arithmetic sequences, we added the difference, the common difference to the preceding term. Whereas when we're working with geometrics, we're multiplying. So we have to multiply the preceding term by the ratio. So this is the recursive formula. Recursive formula for geometric sequences. So keeping that in mind, let's do a little bit of practice. So for number 11, Trey, I'll let you start us off here. So number 11, they give us A1. So the term at position 1 is 3. Our ratio is 2. And they want to know the first 5 terms of the following sequences. So they've already given us the first one. So now the one we're calculating, the term that we're trying to calculate is the term at position 2. And so using the formula I just gave you, what is the term at position 1? Times the ratio. Which is? Yes, there we go. I know, it's so easy, we overthink it. And therefore the term at position 2 is 6. Yes. All right. So Matthew, what's the term at position 3? Write out the formula. What's the term at the previous position? Right. And what's our ratio? Which means that the term at position 3 is 12. I know. All right, Rachel, what about position 4? It's what times what? 12 times 2, which is 24. And then we need our last one, Hannah. It's 24 times 2. I'm making up numbers. So it's 48. Okay. We all remember this? Yes. Okay. Let's do number 13. All right. So picking up with you, Braylon, number 13 gives us the term at position 1 is 6. And the ratio is 4. All right. So they've given us A1. So that's the first part of our sequence. So the term at position 2 is what times what? 6 times 4, which is 24. All right, Genevieve. Why did I put 1? That's position 2. The term at position 3 is what times what? 24 times 4. So that's what, 96? 4 times 20 is 80. 4 times 4 is 16. 80 plus 16 is 96. Yeah. So, Brianna, next one. 96 times 4. So that's 360 plus 24. 384. 384. Noah. He's like, why you do this to me? Well, what's our formula? Yes. Which is 1,536. I'm sure you're right. You did that?
Wait, I say I did that?
Yeah. Oh, I did that. I done that. Makes your English teacher twitch. But she's not here right now. Nope, done. It's I did that. They done. All right, so 23, 25, and 27. Yeah, you would say I have done. It's past participle. But like I said, your English teacher is not here today, so we're not gonna worry about it. Okay. So number 23, I think we're back to you, Trey, right? So no, I'm skipping 17 through 22 because they're just repeats of what we just did. They're just a little more complicated. We'll work on that a little bit later, maybe if we have time. 23 gives us the sequence, and we need to create the recursive formula for that sequence. So 23 is 3, 6, 12, 24, and 48. Did we just do this one? We totally did. No worries. So, Trey, we need a recursive formula. So we have A at position N equals what? So it's this guy here. AN equals AN minus 1 times R. So let's define our, really all we need to do is define our ratio, right? What's our ratio? Right. So what you can do to determine your ratio is take your second term in the sequence, divide it by your first term. 6 divided by 3 is 2. If you want to double check and make sure this is a geometric sequence, you can take 12, which is our term at position 3, and divide it by 6. And you see that you also have 2. So your ratio, you now know, is 2. So then plug that in, and you end up with A excuse me, A of at any position n equals the previous position, nope, times what? R, which is 2. So our equation is AN equals 2 AN minus 1. But what with our recursive formulas, what do we also have to have in order to find the value of a term? That's why we call it a recursive definition, because we also have to define what position. Yeah, we have to have a value for the term. We have to know what the term is in position 1 in order for this formula to work. So this is your entire recursive formula. Yes. Yeah, if it asks you to write a recursive formula, you also have to define your first term. So you have to give a value for the term in position 1. All right, Matthew, number 25 gives us -2, 8, -32, 128, and -512. Y'all check me. Did I write that right? -2, 8, -32, 120. Yep, that looks right. Okay, so first, you can do whatever you want to, but first we need to, or what I mean is you can calculate whichever one you want. You need to know your A1 and you need to know your ratio. Yeah, I like to start with A1 because that's the easiest. It's right there in front of you. So A1 equals -2. Now to determine our ratio, it is -4. But let me just show y'all how you determine that if it's not immediately obvious to you. Take your second term, 8, divide it by your first term, -2. And you find that -2 goes into 8 -4 times, right? Because a negative times a negative is a positive. So first off, you need to see in your sequence, because you're going from a negative to a positive to a negative to a positive, you're going to be working with some sort of negative ratio. So yeah, that's right. So the ratio is -4. So our formula is what? With A1, yeah, with A1 defined as -2. You could also write this, which I feel like is neater, especially if we're multiplying. Whenever we have a constant term and a variable, we always put the constant first. So I would just flip this to be -4a n minus 1. Same thing. We just use the commutative property of multiplication to flip. And so that we put the constant first, which is, what do we call a constant in front of a variable if they're part of the same term? A coefficient, yes. I was talking to Miss Spencer in her Algebra 2 class, has no idea what a coefficient is. I said, well, I'm trying to continue to remind my kids, so hopefully, oh no. So yes, we call that a coefficient. But these mean the same thing. And then of course, include your definition for your first term. Okay. Last one here, 27. Rachel, we are given the sequence -2, -10, -50, -250, and -1250. You see that right? Yep. So the ratio is 5. And we got that by, we took -10 divided it by -2. A negative divided by a negative is going to be a positive. And the fact that all these are negative means that our ratio is definitely positive because we're not alternating. And then A1 is -2. So our formula is what? Times 5. Or AN equals, yep, with A1 or the term at position 1 being defined as -2. And that's it. So now if you see a sequence, you know how to create a formula. If you see a formula with a defined first term, you know how to create a sequence, right? So remember when we first looked at this, how crazy it looks? A with these weird subsets and then numbers everywhere. But now you can see how the different parts work with each other to give you a geometric or an arithmetic sequence of numbers. So once you understand it, it's kind of fun. Because it always works. And even though it looks kind of scary at first. Okay, so let's look at explicit formulas really quick, and then we'll work on some additional problems. So back to page 160. You can see in the box there, they've given you, this should all look pretty familiar from the last section. They give you the position of the term, and then they give you the term. So position of the term. And what do they call it? Just, okay, fine. Got my article. I'm just gonna pick up a couple of these, huh? I know, it's a good thing your English teacher isn't here. I definitely need to add more. She ain't here yet. Ooh. She's trying to come out. I feel like I have multiple personalities. Oh, Nelly. Okay. So if they give you the term at position 1 is 3, and then the term at position 2, what do they give you? So they give you a sequence. They give you your ratio is 2. So to find the term at position 2, you take your previous term, you multiply it times the ratio, which in this case is 2. And remember, if you have a variable with no constant in front of it, what is the understood coefficient? 1. If you have a variable or a number with no exponent, what's the understood exponent? 1, right? So we have to kind of remember those, that really when we're defining that second term, we're just multiplying 3 times the ratio at an exponent of 1, which gives us 6. Just write this. So this is our given. 3. Okay, so term 3 is just 3 times the ratio with the exponent of the previous position. So it becomes 3 times 4, which is 12. And then 3 times the ratio at exponent n minus 1 is 3 times 8, which is 24. To any number. So this means that the position of any term at, excuse me, what am I trying to say? The term at any position n is the first term, A1, times the ratio with exponent n minus 1. And that's what they're showing you right there this is just a recreation of the table that's already on page 160. So you remember when we were working with algebraic not algebraic, I'm sorry, with arithmetic sequences, we multiplied the difference times the previous position, n minus 1. Well, now because we're working with a geometric sequence, which already has multiplication, you move it to the next level, which is exponential. So instead of being multiplicative, it becomes exponential, which is what we see here. Let me show you the formula, and then we're going to play with it a little bit so you can understand what I'm talking about. So the explicit formula for a geometric sequence is the term at any position n equals the first term in the sequence times the ratio with the exponent equal to the previous term, n minus 1. I'll put a little multiplication in there because with all these exponents, you know, subsets, it can get a little confusing. Where A1 equals the first term of the sequence and R equals the common ratio. All right, that's what we're looking at right there in the middle of page 160. And then they give us an example. So in this case, they want us to write the explicit formula, and they've given us a sequence. So example 5. What? Oh, I need to go check lockers. I mean, y'all know which locker Grace, well, Grace is not here and Amy's not here. So I need to check their lockers and just make sure there's not a book in one of them. But yeah, if not, I'll make you guys a copy. Remind me, because I keep forgetting. All right, so the sequence they've given us is -5, -15, probably -45. Yep. They gave us one more. -405. See how these geometric sequences, they escalate quickly. Because this is how I would say. All right, so our explicit formula, AN, this is our base formula, equals A1 times R to the ratio equal to the previous position. And then we just define our parts. So what's A1 in the sequence? All right, so A1 equals -5. What's our ratio? Yep, just, I'm going to calculate it out for us. -15 divided by -5 equals a +3. So when we plug that into our formula, we find that the term at any position equals A1 -5 times 3 raised to the yes, it is an exponent. All right, so let's actually look at this where we can calculate it. They don't really let y'all do that, but I feel like it would help if you could actually calculate one. Probably because they become really big. So at this point, we're just writing the formulas. We're not actually solving them for a particular or a specific position. So let's try to do skill check. What is this number? Skill check 3. All right. So what it's asking is for you to write the explicit formula for the following sequences. So we'll do, actually, you guys try number 1. We'll do number 2 together. I'll give you all like 2 minutes. You have the formula, calculate A1 and the ratio, and then plug them into the formula. You pause this. Resume. Okay, so if we're working through number 1, then we calculate A1, calculate R, and then plug them into the formula AN equals. So what is A1? 2, right? What is our ratio? Right? 8 divided by 2 is 4. So it's a positive 4. So our formula is AN equals what? Right. So the term at position N, AN, equals 2 times 4 raised to the power of the previous position, or N minus 1. It's really hard to say. Now, why can't you simplify this? Why couldn't you go ahead and do 2 times N, which is, or 2 times 4, which is 8, raised to the power of N minus 1? Right, because order of operation, you would have to, because 8 to an exponent is a whole different number than 2 times 4 raised to an exponent. So, let me actually, let me put another step on this. So tell me the term at position 15. So if I'm trying to, if I give you, tell me the term at position, now this is calculator worthy right here for sure. Actually, let me get my big calculator so I can do exponents a little easier. So how would this look? Where am I plugging in all these numbers? So the term at position 15 equals what times what raised to the power of what? 2 raised to the power of, right, so it's 2 times 4, well, and you, yeah, whatever, we'll do this, 4 to the power of 14. So is that what you said?
Well, I said 8 times 14. I was like,
not 8 times 14. It's 4 to the power of 14. So it's 4 times 4, 14 times. 4 times 4 times 4 times 4 times 4 times 4 times till you get to 14 fourths. So you plug that into a calculator. What do we need to calculate first? According to our order of operation, we got to, 4 to the 14th power. So 4 raised to 14. This is so huge. Okay, that's okay. We'll do this. So it equals 2 times 2684 354 56. I told you, exponents escalate quickly, very quickly. So that times 2 means, yes, the term at the 15th position of a geometric sequence with only a ratio, well, it's got a ratio of 4, which is probably why it's so big, is 5, 3, 6, 8, 7, 5, 3, 6, 8, 7, 0, 9, 1, 2. So it is, oh gosh, let's see here. All right, we're still in the millions though. I know, right? 536,870,912.
I wish I had that baby account.
You want that bank account? Me too, girl. I split it with you. All right, I just threw that in so you guys can see what this looks like actually plugged in for a specific position. All right, so let's move on to number 2 because we're gonna run out of time if I keep playing. All right, so number 2 we have negative 250. And then we go down to 50. And then not 15, Meredith. Lord have mercy. 50. And then we have negative 10. 2. Don't even start. So we have two things we need to notice about this geometric pattern. What's the first thing?
The ratio is going to be negative.
The ratio is going to be negative. Is that what you were going to say, Genevieve, or did you notice the other thing? Yes. Okay. So first off, we know that our
No.
oh
It's going to be a negative fraction.
yes. The other thing you need to okay, we'll get to that in a second. The other thing we need to recognize is that these numbers are getting smaller. As we move through the sequence, they're getting smaller, which means we are multiplying by a fraction, which is the definition of division. When you got the answer that you got? Yeah, because you were right. So we know that this is going to be a fraction, a negative fraction. So it is negative 1/5.
You said I'm so surprised. Yeah.
Yes. So what you need to understand when you look at this is that the alternating negative and positive means you're going to have a negative ratio, and the fact that it is decreasing in value means you're going to have a fraction, because you are 50 is a fraction of 250. Let's actually do the math for that though. So you take the term at position 2 and divide it by the term at position 1. Now, if I'm not using a calculator, I like to do these in fraction forms. So I would put 50 divided by negative 250. Now, I know because I have a negative in my denominator, but not in my numerator, that my answer is going to be negative, right? Because well, I did in this case because on my sequence, my 250 was negative. That's why I put it there. If my 50 was the negative one, I would have probably put it in the numerator. Excuse me. So we know that 50 is smaller than 250. So I would add a decimal. 250 doesn't go into 50, so that's 0. But 250 goes into 500 how many times? No, not 5 times. How many times does 250 go into 500? No, 2. 2. No, I did too. My brain sort of shut down when you said 5, and I was like, that's not right. But why is that not right? But yes, so 250 times 2 equals 500. So 250 goes into 500 2 times.
I thought that was wait. 250 times 25.
But we're not doing 5 times 5.
I know. 2 times
5 times 5 is 25, but 5 times 10 is 50. How many times does 25 go into 50? 2 times. Think about quarters. I don't know. I somehow just broke y'all. We got to remember how to figure out our fractions. So if you see a decimal of 0.2, that is 20 over 100, which is 2 over 10, which is 1 over 5. So that's how we got this negative 1 over 5 as our ratio. And somehow, I'm sure, and somehow that just broke y'all's little brains. Sorry. So what's our A? Let's move on though. What's our A1? What's our term at position 1? Therefore, our recursive formula is AN equals what? Negative 250 times negative 1/5 with the power of n minus 1 with a1 defined as, wait a minute. Do we need that? That's right. We're doing explicit formula. My bad. That's why we don't need to define a1. We already have. I got so distracted. I forgot. Okay, so that's our explicit formula for this sequence. All right, so let's do 3, 4, and 5 really quick. These should be pretty easy. Looking at sequence 3, we have 81, 27, 9, and 3. So for all of these, we need to determine, is the sequence arithmetic, geometric, or neither? 81, 27, 9, 3. Is this geometric or arithmetic? It's geometric, right? Because your difference, you don't have a common difference, but you do have a common ratio. Each one is multiplied by a third. So this is geometric. Number 4 gives us 6, 10, 14, 18. Geometric, arithmetic, or neither? It's arithmetic. Why can I never spell arithmetic?
Geometric.
Arithmetic. Oh. There you go. That works. What did you just ask me? What makes it geometric? What's the difference between geometric and arithmetic? Arithmetic is adding and subtracting, which is why it uses a common difference. Geometric is multiplying and dividing, which is why it's a common ratio. Yes. That felt important. I knew you were just sort of having a moment, but I felt like I should address it because they can both descend in value. It just means it's subtraction or division instead of multiplication or addition. All right, last one. 2, 22, 222, 2,222. What's your common ratio? 2 times 11 is 22. What's 22 times 11? It's neither. Yeah, this is neither. Definitely don't have a common difference because the difference between 22 and 222 is much bigger. It's 200, whereas the previous one is 20. And you don't have a common ratio because there's not a common number that each preceding term can be multiplied by to give you the next term. So in this case, this is neither. It's something else.
I love that. It's something that we're open on, like
Maybe.
oh.
All right, so let's work on some additional problems. I know we only have about 10 minutes, but I want to do, or we could do nap time. No. All right, let's do, okay, in this case, I want the first, so these are additional problems. These are not in your book. So these will be good to jot down so you have them for reference. So our first one here, I want the first 4 terms of this sequence. If I give you A1 equals 2, and your recursive formula is A at position, or the term at position N equals 4 times the term at the previous position. What's my term at position 2? They've already given us 1. Hmm? 8. So it is 4 times the term at position 1, which is 8. All right, and then the term at position 3 is 4 times 8. We're using recursive. 32. It's yeah, escalating quickly. All right, so the term at position 4. It's because we have a ratio of 4. So every time it's a number divided by 4. Right. 128. And last one, 4 times oh, they told us to only calculate the first 4, but we can do this. 4 times 8 is 32, carry 3. 4 times 2 is 8, plus 3 is 11, carry 1 is 512. You were right, 512. All right, so for this one, tell me my common ratio of this sequence. 4, -12, 36, -108. Your common ratio, otherwise known as R, equals -3. Right, we know it's negative because it's alternating from positive to negative. And we know it is a whole number, not a ratio, or excuse me, not a fraction, because the numbers are getting larger. All right, last one. Give me the explicit formula. If, let me find myself. Your sequence is -3, -6, -12, -24, etc. AN equals what's our base formula? AN equals A1 R to the power of, yeah, N minus 1. Y'all like that expression, don't you? Raised to the power? Yep. Yeah. Or a lot of times we shorten it just to the power of whatever. All right. So A1 is -3. Determine that. What's our ratio? All right. 2. Yeah, because we don't know what N is at this point. So AN equals -3 times 2 to the power of the previous position, which is N minus 1. All right. All right. That's it. We're done. We will spend some time following up on this. I think I need to take a look at your quiz, but we need to have some practice working on the word problems. But at this point, we should have a quiz coming up. So I'll have a quiz review for Monday. And then we can plan on having a quiz on sections 4.5 and 4.6 on Tuesday. All right.